In chapter 2, we're going to dive a little bit more into matrices, and we're going to look at operations, some properties of matrices, and then we're going to get into the inverse matrix, and then we're just going to do some fun stuff at the end of this chapter with cryptography and coding. So let's start. Let's talk about the definition. When we talk about a matrix, remember we said we could define any element in the matrix in terms of its rows and columns. So let's say we have a matrix A, that's let's just say it's a 2 by 2 matrix, just being real generic here. So this would be the item in the first row, first column. This would be item in the first row, second column. This is the item in the second row, first column. And this is the item in the second row, second column. So we can always identify a matrix by its elements in the matrix. Each item in there is called an element. And we can identify that element by the row and column that is in. The row number is always first, the column number is always second. So when we talk about this definition, they're defining matrix A in terms of the element. So instead of writing out this gigantic matrix that has just a whole bunch of very generic elements in it, because remember, this guy's just a 2 by 2, but now we're talking about any size. It could be a 3 by 4, it could be a 17 by 21. So we're talking about any size. So instead of writing that out in a gigantic form, we can simply condense that mathematically and write it in terms of each item identified by its row and column and where that lives. So we have a matrix that can be written condensedly this way, and we have a B matrix that can be written condensedly this way. Both of the matrices are of the same size, and it's an M by N matrix. To define the sum of the matrix, what this is telling us is that each matrix has to be the same size, and then to find that sum, all we do is we add elements that are in like places. Notice that we've got IJ here and IJ here. So addition is really easy. You just add things that are in the same place. So for example, let's say we have a matrix A and B. So if we want to add matrices A plus B, they have to be the same dimensions. So this guy is a 2 by 3, this guy is a 2 by 3. Since they're the same dimension, then we can add them. And all you do is you add like terms. So what's in that top left-hand corner, that's the A11 and the B11 slots. You just add those numbers together. So we're going to get a -3. And then we're going to move to that next term. That's the A12, B12 slots. Add them, you're going to get +3. Then we're going to look at that top right-hand corner. Add them, and we're going to get an 8. Bottom lefts. Add to get a 2. Bottom middle. Add to get a 3. Bottom right. Add to get a 7. So that's how addition works. Now, subtraction is just a fancy addition, right? Because we could rewrite this as plus negative. So subtraction is really going to work the same way. I'm going to leave it as a minus here. That order is important. A has to come first. So in this case, we're going to have 1 minus -4, which will be a 5. We have 2 minus 1, which is 1. 3 minus 5. 2 minus 0. 1 minus 2. And 4 minus 3. So as long as the matrices are the same size, you can add them and you can subtract them. Notice you're going to get whatever size that is. We started out with 2 by 3s. We're going to get a 2 by 3. That's forever and always. Scalar multiplication means that we have some number, and for now we're going to talk about real numbers, that's in front of that matrix. So then the way we do scalar multiplication is that we just multiply that number into each entry. And that's what this notation is talking about. Notice A is identified by every element in there. So if we have a number times matrix A, then that's the same as distributing that number to every element in there. So if we wanted an example of that, let's say we wanted 3 times matrix A. Well, for us, if our A is this A up here, it's going to be 3 times the 2 by 3 matrix. 1, 2, 3, 2, 1, 4. So we're just going to multiply that 3 into each entry in here. So we're going to have 3, 6, 9 across the top, 6, 3, and 12 across the bottom. So there's scalar multiplication. We can multiply positive numbers. We can multiply negative numbers. Let's say we have negative 2 times B. For us, that's going to look like this. So we're going to have 8, negative 2, negative 10, 0, negative 4, and negative 6. And then if we wanted to, we could even put this kind of stuff together. Suppose we wanted 3A minus 2B. Well, then we would have 3 times matrix A minus 2 times matrix B So there's your setup, and your rules are the same as your rules if we were just dealing with row numbers. Order of operations still apply. We would want to do the scalar multiplication before we dealt with the subtraction. So if we were to multiply that 3 in, we would have that matrix, subtract, and I'm going to multiply that positive 2 in since I'm keeping the subtraction here. So 16, negative 4, negative 20, 0, negative 8, and negative 12. And then if we were to subtract, remember we subtract like components. So 3 minus 16 is negative 13. 6 minus negative 4 is 10. 9 minus negative 20 is 29. 6 minus 0 is 6. 3 minus negative 8 is 11. 12 minus negative 12 is 24. Now notice we started with 2 by 3 matrices here and here. We did scalar multiplication first. We still had a 2 by 3 matrix. And we ended up with a 2 by 3 matrix. Anytime you're adding, subtracting, or multiplying by scalar, you will always have the same size that you started with. Now, multiplication is a little bit more interesting. So we're going to look at the sum of a bunch of stuff, and there's an algorithm that goes along with this. So we have matrix A, matrix B is identified this way. If we want to identify the product of that matrix, and they're writing that product, they're calling this matrix C, by the way. We're going to end up with a matrix that's going to have possibly different dimensions. If A is an M by N matrix and B is an N by P matrix, notice that the dimension of the column in the first matrix is the same as the number of rows in the second matrix. Then you're going to end up with a matrix that is M by P in size. So this matrix size could change depending on how big your A and your B matrices are. And it's also possible that matrix multiplication won't even be defined. So what happens is we move across and down rows So let's look at a few examples. I'm going to create some new A and B matrices. So check out what's happening. A is a 2 by 2 matrix. B is a 2 by 3 matrix. So look what's going on. Notice that the number of rows in B and the number of columns in A are the same. Those inside dimensions have to match in order for matrix multiplication to be defined. And what's going to result will be a 2 by 3 matrix. So if we look at matrix multiplication, we know we're going to get a 2 by 3. So I'm going to go ahead and put all my little slots in here. You'll see why in just a minute. So I have a 2 by 3 matrix that's going to result. 2 by 3. If I want the entry in that first row, first column, so I'm looking at what's going to go here. I'm going to have to use first row, first column to get there. So I'm going to multiply 1 times 0 plus 2 times 4. So I'm moving across that first row and I'm moving down that first column. And I'm going to add. That's what this algorithm is trying to tell us here. So you're going to multiply those entries together as you move along the row and column. And if we do that, we're going to have 0 plus 8, which is 8. So we've got the entry in the first row, first column. Now let's find the entry in the first row, second column. So we're going to end up using that first row in that second column to get there. And we're just going to multiply those first terms together. So this is going to be a 1 times 2 plus, and then we're going to multiply 2 times 1. And that's going to give us a total of 4. So you can kind of see how this is working out. Now let's go to this. This is first row, third column, which means you have to use the first row and you have to use the third column. So we're going to have 1 times 1 plus 2 times 5. We're moving across the row and down the column. You multiply, add, and so on. So we're going to have 1 plus 10 is 11. And now we're going to move to that second row. So we want the entry in the second row, first column. So we're going to use that second row in that first column. So it's going to be 3 times 0 plus 4 times 4, which is 16. So now we need this guy, second row, second column. So we're going to use second row, second column. Multiply, add, multiply, add. And then now we're in the second row, third column. So we have to use the second row and we have to use the third column. So we're going to have 3 times 1 plus 4 times 5. And that's 23. So there's our product AB. Notice that guy was a 2 by 3. So what's interesting about matrix multiplication is that it is not commutative. And what that means is that we can't just multiply in any order. That order is going to be super important. And in some cases, that order may not even be defined. So let's look at this one. I'm going to change my color so you can see this in a different color. Suppose we wanted BA. We wanted to change the order. Well, matrix B is this one. Matrix A is this one. So notice we had a 2 by 3, and then we have a 2 by 2. Do you see how those inside dimensions don't match? If they don't match, then the matrix multiplication is not defined. So that means this just does not exist. Okay, and the reason is the algorithm falls apart. Look at what happens if you try to multiply. You would have 0 times 1 plus 2 times 3 plus 1 times what? What would you have to multiply that 1 by? You run out of numbers in that column of the second matrix, which means that there's just not a defined multiplication for that. So that's where the algorithm's going to fall apart. So it just doesn't exist. Let's do another one. So we have a 2 by 3 here and a 3 by 2 here. So this one's going to be pretty interesting, and it'll also show that commutativity property falls apart for multiplication. So if we look at C times D, so we have 1, 2, 3, 2, 1, 4. I'm just going to recopy here. And then 4, 0, negative 2, 1, 5, 0. So we have a 2 by 3. And then we have a 3 by 2. Okay, notice inside dimensions match. That means we're going to result in a 2 by 2. It's always whatever's left over on the ends there. So our sum will be a 2 by 2, which means we will have 2 rows and 2 columns, 4 entries. So if we were to write this out, I'm going to make this a little bit bigger. So I need first row, first column. First row, first column. So we're going to have 1 times 4 plus 2 times negative 2 plus 3 times 5. So 4 minus 4 plus 15 is 15. And now I need this entry, which is in the first row, second column. So I have to use first row, second column. So we're going to have 1 times 0 plus 2 times 1 plus 3 times 0, which is just 2. Now I need this guy, which is in second row and first column. So whatever row and column this is in will tell you what row and column you use in those matrices. So we're going to have 2 times 4 plus 1 times negative 2 plus 4 times 5. So 8 minus 2 plus 20, 26. And then we need the last entry, which is in the second row, second column. So 2 times 0 plus 1 times 1 plus 4 times 0, which is just 1. So there's our product. Notice this guy's a 2 by 2. Now, if we were to change the order here, suppose we wanted D times C now. Well, let's write out what that would look like. So matrix D is 4, 0, negative 2, 1, 5, 0. And matrix C is 1, 2, 3, 2, 1, 4. So when we did CD, we got a 2 by 2. But if we look at this one, the matrix multiplication is defined in this case, and we end up with a 3 by 3. So not only is matrix multiplication not commutative, which means order is important. We can't multiply in any order and get the same thing. But we may get something that's not defined. or we may get something that's a completely different size. So take a few minutes. You may want to pause this video, try this one on your own, and then come back and check your answer. So we're going to have 4 times 1 plus 0 times 2, which is a 4. First row, second column, we're going to have 4 times 8. Just kidding. I'm multiplying already. 4 times 2 plus 0 times 1, which is 8. Then we're going to have 4 times 3 plus 0 times 4, which is 12. Second row, we're going to use second row, first column. So negative 2 times 1 plus 1 times 2, which gives us 0. We're going to have second row, second column is negative 2 times 2 plus 1 times 1. Negative 4 plus 1 is negative 3. Negative 2 times 3 plus 1 times 4. So there's negative 6 plus 4, negative 2. 5 times 1 plus 0 times 2 is 5. 5 times 2 plus 0 times 1 is 10. 5 times 3 plus 0 times 4 is 15. So there's your product matrix. So we can use these properties to help us solve, some basic matrix multiplication equations. So let's look at 55. We have a 2 by 2 here, and this is also a 2 by 2, and we're going to result in a 2 by 2. And this makes sense because that multiplication is defined, and that's going to give us a 2 by 2 as that product. So let's multiply this out. If we multiply out, we're going to get a 2 by 2. So we're going to have 4 entries. So we're going to have 1 times A plus 2 times C. So 1A plus 2C. Now we're going to use first row, second column. So we're going to have 1 times B, which is B, plus 2 times D, which is 2D. Now we're going to use that second row, first column. So 3A plus 4C. And then for that last entry, we need to use the last row, last column. So 3 times B plus 4 times D. And that's going to be equal to that matrix 6, 3, 19, and 2. So now we have a system. The only way these equations, these matrices are going to be equal is if what's in the top left-hand corner on the left matrix equals the top right-hand corner on the right. So we have A plus 2C has to equal 6. That's the only way that's going to work. Same thing here. This guy has to equal that guy. It's the only way these two could be equal. So we have B plus 2D has to equal 3. And then we have this has to equal that. So 3A plus 4C has to equal 19. And then 3B plus 4D has to equal 2. So we've got this system of equations that we can solve. So A column, B column, C column, and D column. A, B, C, D. There's your first equation. Second equation. Third. And fourth. this is where you may want to pause the video if you want to. Try doing Gaussian and Gauss-Jordan elimination. See if you can come up with the solution. So the first thing I would want to do is take row 3 and replace it with row 3 plus -3 row 1. Notice row 1 staying the same. Notice row 2 staying the same. So row 3. So we're going to have 3 plus -3 times 0. 0 plus -3 times 0. 4 plus -3 times 2. 0 plus -3 times 0. And 19 plus -3 times 6. And row 4 stayed the same. So now I need to zero this guy out, and I'm going to do that using that second row. So we're going to take row 4 and replace it with row 4 plus -3 row 2. So we have 0 plus -3 times 0 is 0. 3 plus -3 times 1 is 0. 0 plus -3 times 0 is 0. 4 plus -3 times 2. And then 2 plus -3 times 3. So I want this to be a 1 here, and I also want this to be a 1 here, but I need to get rid of this, and I need to get rid of this. So I could do it with fractions, or there's lots of things you could do here. Here's what I see. I see I could go ahead and knock this guy out by using that 4th row. I also see I could knock this guy out by using that 3rd row. And it's not going to affect those zeros that I have in key places. So let's do that. So it's all about really just identifying what you have, what you need, and where you need to go. So I'm going to take row 1 and replace it with row 1 plus row 3. And then I'm going to take row 2 and replace it with row 2 plus row 4. And that's going to give me, I believe, that identity on the left. Let's do it and see what happens. Row 1 is going to be row 1 plus row 3. So 1 plus 0 is 1. 0 plus 0 is 0. 2 plus -2 is 0. 0 plus 0 is 0. And then 6 plus 1 is 7. Row 2 is row 2 plus row 4. 0 plus 0 is 0. 1 plus 0 is 1. 0 plus 0 is 0. 2 plus -2 is 0. 3 plus -7 is -4. And then we did not change the last 2 rows. So I'm just going to recopy. So we're deviating slightly from the algorithmic way to do Gaussian elimination, just to avoid some fractions that can get a little tedious. And that's perfectly fine. And now we're going to finish this guy off. Row 3 is going to be -1/2 row 3. Row 4 is going to be -1/2 row 4. So we're going to have 1, 0, 0, 0, 7 across the top. 0, 1, 0, 0, -4 across the second row. 0, 0, 1, 0, -1/2 on the third. 0, 0, 0, 1, 7 halves along the bottom. So we know A has to be 7, B has to be -4, C has to be a negative 1/2, and D has to be 7/2. So then our matrix would have to look like this. There's our answer to that particular problem.